Hello, and welcome to Economics 320. In this video, I'm going to do a little bit of introductory material, and so just some general things about regression models. And chapters 2 and 3 are about probability and statistics. Those will be in the next video. That material ought to be reviewed. You should have had a probability and statistics in the prereqs for this course. And so I'm just going to cover the highlights of those two chapters, the things we'll really need to go forward. If it's been a while since you've had that stuff and you've forgotten, you're probably going to want to read those chapters in depth. If it's pretty familiar to you, maybe you can get by just with the things I do on the video. I'll really leave that up to you. But again, I'm not going to do the second two chapters, 2 and 3, in depth. And we'll really get started in the course with chapter 4 on the two-variable regression model. Okay, so what are we going to do in this course? Well, the main point is to figure out how to do the following. And so, first of all, I want to know how to formulate hypotheses. From theory. So theory might tell us that the relationship between investment and the interest rate is negative. How can we test that particular hypothesis? It might tell us that the MPC is between 0 and 1, the marginal propensity to consume. How do we test that? Theory might tell us that if government spending goes up, it raises interest rates. Or if money supply goes up, it lowers interest rates. Is there a way that we can look at the data on those things, on government spending and interest rates, and test those hypotheses? So we can test both specific values, something like, is the MPC equal to 0.9? We could test that. Or we can test signs. Is the MPC positive? Is the coefficient on the interest rate, when I look at the relationship between investment and the interest rate, is that coefficient negative? And so we'll formulate those hypotheses from theory, the things we're interested in testing. Then we'll go out and we'll collect data. Maybe we're interested in the relationship between consumption and income. So we collect data, and we could plot those. Here's income. Here's consumption. Here's income. And then we could plot those data on using some graphing software. eViews, which we'll be using to estimate these models, will do this for us. And so we can plot these data and say, well, it looks like there's a positive relationship between those two variables, but what's the best fitting straight line through those variables? How can we estimate the model, the line? That's supposed to be a straight line. My hand's a little shaky because I'm nervous in the first class or something. How can we estimate the line that's closest in some sense to all of these points? And that'll be called the regression line. So once we have the data, got a hypothesis, collect the data to test it, then we'll run a regression. And it will allow us to test to find the coefficients. So we'll find the slope and the intercept. We have a line like CI is A plus B times YI plus, we're always going to have an error term, error I. And I'll split these I's just index the number of observations. So I might have consumption and income for 1,000 people. I would tell us which person. I would go from 1 to 1,000. This error term is just picking up the fact that the points don't hit right along the line. The further these points are from the line, the bigger the error will be. And one of the things we'll learn how to do is characterize how well the line fits the data. Does it fit it really well? Are the lines really close to the data? Are the data really close to the line? Or are the data more spread out, way out in here, like, all over the map? Then the error term is relatively big, and we'll be able to detect that our fit isn't so good. But we'll run these regression lines, and it will give us specific numbers for the slope and the intercept. Then we could test. Maybe we want to know, is the MPC equal to 0.9? We could say, in these data, is B, the estimated value we get from the regression, close enough to 0.9 that we're willing to say, yeah, it looks like that hypothesis is true? Or is the value we estimate we estimate it to be 0.2. Is that so far from 0.9 in these data that we're not willing to say that the hypothesis is true? So we'll be able to reject hypotheses or fail to reject based upon these estimated models. So formula hypothesis, collect data, estimate a line, then we can run the regression, then we can test the hypothesis. Is beta greater than 0? Maybe we just want to know if beta is positive. Is it? We can use our estimated model to test those sorts of things. The other thing we can do with these regression models is forecast. So we can either use models to test hypotheses, or we can use the model, the estimated model, to forecast. We could say, what if income was this? What would consumption be? What if income was this? What would consumption be? Maybe we've estimated a monetary policy equation. We could say, well, if the Fed raises the interest rate by 1%, what would happen to investment, employment, unemployment, income, those sorts of things? If government spending goes up, what happens to employment, to output, to interest rates, to prices and inflation, all those sorts of questions. And so we can use the model to forecast, and sometimes those forecasts will, and often in economics, those forecasts will be policy experiments. What would happen if we raise taxes by this amount? What would happen if we change government spending? And so it's a lot of what-if questions. Now, after the introductory material, including the stuff in chapters 2 and 3 on probability and statistics, we'll go on to chapter 4, and we're going to start with a 2-variable regression model. So we're going to start very simple. And in general terms, those will look like yi. This is how we're going to write our model, is beta 0 plus beta 1 xi plus ei, or ei is the error term. Now, sometimes we'll use different terms for this error term. Don't worry about that. We'll get to that later. This is the general form of the regression models that we're going to be looking at. And we're interested in estimating beta 0 and beta 1. Now, just a second ago, I had CI here and YI here. That's because Y was income. This is just some general Y and X. And I want this to be in this form. I'm going to have XI on this axis, YI on this axis. Maybe the relationship this time is negative between these two variables. So we have a bunch of data that look like this. We fit a line to it. And we're going to be able to estimate this beta 0 and this beta 1 term, and also estimate how big the errors are. Once we know the line, because we know what each of these points are, those are just our data points, we can figure out how far away the points are from the line on average, and that'll be a measure of fit. But so we'll first learn out how do we estimate this model. And we'll have a formula for that will also just come down to putting the data into your eViews program and then punching a button that gives you beta 0 and beta 1. So we'll learn how to do it both theoretically with formulas and also just by pushing the button in our regression model. Now, sometimes 2 variables are not enough. Suppose, go back to that example of consumption and income. Well, maybe consumption doesn't just depend upon income. Maybe it depends upon taxes. Maybe it depends upon interest rates, especially things like consumption of things like cars and refrigerators. We have to borrow money. And so it may be that if we want to figure out what a variable, if we want to model this variable, we need more than 1x. So this would be a 3-variable model. This could be consumption, income, taxes, interest rates. And we'll learn, this is a multiple regression model. Is that how they say it in this book? Let me make sure. Yeah, regression where there's more. This is called multiple regression. We'll learn how to estimate these multiple regression models, and we can have any number of x's if our data set's big enough. We can't have more x's than data, something we'll come to later. But as long as you have less x's than data, you can estimate any number of these. So in general, we'll write this as yi is, oops, this should have been beta 0 right here. That's a typo. Beta 0 plus beta 1 x 1i plus beta 2 x 2i plus beta k x ki plus ei. In this example, up here, k equals 3. In our first example, k was just equal to 1. That was a two-variable regression model. So we'll learn to estimate these multiple regression models, multiple variable regression models. That way we can explain why, with as many things as we need, government spending doesn't just depend, interest rates don't just depend upon government spending, they depend upon the money supply and all sorts of things. And so often theory will tell us what variables belong in our model. If I'm running investment on interest rates, maybe I want business confidence maybe affects interest rates too. So I might want data on business confidence or investment. Investment wouldn't just be a function of the interest rate. It might also, investment might also depend upon business confidence. It may also depend upon GDP. It may also depend upon some other things. And so we can put all the things in here that explain investment. And then if this is the interest rate, then we can focus on this beta 1. But it'll be important, as we'll see, that we get all the variables in the model that we need. Because if we leave things out, often that will cause the coefficient that we estimate to be biased. Getting ahead of myself a little bit here. So we're going to learn to estimate these two variable models as a first step. Then we're going to estimate these multivariate models because those are more realistic formulations of economic theory. It's rare that we just get a bivariate relationship. And so we usually need these multivariate relationships. Then we'll go on and learn a little bit about how to do, how to handle nonlinearities in the data. So suppose that y and x are related in a way that looks like this, in a nonlinear fashion. Is there some way that we can use our linear regression model to get at these questions? It turns out often we can. And we'll talk about how we can estimate those nonlinearities in simple linear models, believe it or not. And so that'll be important. We'll learn how to log variables and add cross-product terms and do all sorts of things that allow us to have some quite complex relationships that stay in a nice linear regression framework. And then we'll learn a little bit more about how to assess models. When do we have a good model? When do we have a bad model? What might go wrong? And those sorts of things. And that'll sort of lead you up to the next course in this sequence, which is 421. In this course, we pretty much assume that the setup, the data that we get will have these properties that make it easy to use. We're going to assume it has all these nice properties. In the real world, those properties aren't always met. What 421 is largely about is what if you don't have these ideal conditions? So we're going to pretend in this course like we've estimated the model under ideal conditions. It's as though we go to a laboratory and we do an experiment and we have perfect data and we use those perfect data to estimate a model and test a hypothesis. In the real world, in economics, we don't do experiments. We'll talk a little bit more about this in a second. We just take the data from history, and those data are often imperfect. And because they're imperfect, they might not be random in the way we need them to be random. There might be some systematic things in there that cause biases. And we'll talk a little bit about how to watch out for those things, but 421 is where you learn how to correct for all these problems that might occur in your data. Okay. So the book goes on at this point to talk about what is econometrics. And they give a bunch of things. Let's define it by what it does. Econometrics is for testing economic theories. It's for forecasting. Econometrics involves forecasting sometimes. It's fitting mathematical models, those regression models we talked about, to real world data. It's about using historical data, these estimated models based upon historical data, to to make policy recommendations. If we want to cure a recession, what should we do to interest rates if we're a monetary authority? Those sorts of things. More generally, the book defines econometrics as follows. It's the science and art of using economic theory and statistical techniques to analyze economic data. And we are going to use, the book illustrates econometrics through 4 main examples, one of which we'll use almost exclusively, the other 3 not so much. But let me look at, so they're going to use these methods to illustrate how to answer 4 questions. So there's 4 main examples in the book that run through the whole thing. The first one is, does reducing class size improve elementary school education? And this is the one we'll look at most of all, and I'll talk about it a lot more as we go through, particularly as we start into chapter 4, where we really get into this particular question. But how can we answer this particular question? We'll see that we need multi-regression analysis. We probably want to put in a whole bunch of other variables. We'll learn how to face certain problems, like how do we measure elementary school education? How do we measure outcomes? Do we use a test score? Is that the right measure that we want? Do we use math scores? Do we use reading scores? If we use both, how do we combine them? Do we just add them up and equally weight them? What exactly is an educational outcome and how do we measure it? Class size, I think, isn't so hard to measure. But again, there'll be a few measurement issues there we'll need to worry about. We don't mean how big the physical space is, of course. We mean the number of people in the class. That one we can measure fairly precisely, but we'll have a little more trouble here. So we'll look at some of the measurement issues and all sorts of things. And as I said, this is the example we'll look at the most. Some of the homeworks will have other examples, and later in the text there's some other examples. Another one that they look at sometime is there racial discrimination in the market for home loans? So how would you write down a hypothesis that could test this? How do you get data? How do you estimate it? All those kinds of questions. The third one is, how much do cigarette taxes reduce smoking? And finally, the fourth question, it's the main example in the text, is how much will GDP grow next year? I think I forgot question marks. Now, these first three examples are about what we call causal, not casual, but causal relationships. We're asking about whether one variable causes another. Does a change in class size cause a change in elementary school outcomes? If so, by how much? If we go from 23 to 22 or 23 to 21 students per class on average, how do you is there a change? Does it matter at all? So is there a causal relationship? Sorry, I was thinking, I said there's no measurement issue with class size, but I'm realizing in a particular school, even if we focus on a particular grade, as this will do, you might have 4 different classes of 5th graders or 4th graders, something like that. They could be different sizes. If I just take the average class size, is that the right way to measure class size? Do I care about the variance? If one is 5 and one is 50, say 55, the average is 30. Is 30 the right measure for the average in that kind of a case? So there's not only do you have to worry about how to write these hypotheses down, but you have to be very careful about how you measure things. And measurements often as hard as measurement's often the hardest part. This one's about forecasting. So here we're testing hypotheses. Does one thing cause another? Here we're just interested in forecasting. And so let's start with talk a little bit about causal relationships, then we'll talk a little bit about forecasting, just in an introductory kind of a way, and then we'll move on. All right, so as I said, the first three, so we're going to start by talking about causal effects and idealized experiments. Essentially what we're doing is we're going to say, suppose we could go into a lab and do experiments and hold everything else perfectly equal and control all this and control all that, do these ideal experiments where we randomize the treatment in a way we'll talk about in a second. What would be the best way to estimate? Now, suppose we don't have an ideal situation, as we often don't in economics because we can't do experiments, we have to use historical data. How can we come as close as possible to that idealized setup? And if we don't have that idealized setup, how can we change the way we estimate? Sometimes we can do transformations of the data or estimate in a different way that gets us back to an ideal situation. Or we can say, what's the closest we can possibly come to the ideal situation given the data that we already have, that we actually have. So the idealized experiments really serve as a benchmark in economics. In the physical sciences, we can actually go to the lab. You can try to set up these idealized experiments. I took a class as an undergraduate. The whole thing was about experimental design, how to design experiments in a way that ensures that you're as close as possible to the ideal setup, the ideal situation. Then your statistics are more likely to be valid. Okay. So by causality, what do we mean? If we want to estimate causal effects, what do we mean by causality? We mean that a specific action, such as taxes going up or more nitrogen going up, leads to, so that arrow leads to a specific measurable consequence. Such as consumption goes down or plant yield goes up. And so the question is, how can we estimate and measure these causal effects? How can we then test for causal effects? So the book has an example that it uses. It says, how can we best measure causal effect, the causal effect on tomato yields and they do it in kilograms, though it doesn't matter what units you measure, you'll still get the right answer, of applying 100 grams of fertilizer. I don't think I used the right gram abbreviation there. Oh well. Fertilizer per square meter. So just think about what you want to do in a laboratory experiment. You'd want to do what? You'd want to take a plot of land. And the more land, the better, because the more times we can do this experiment, the better. So what we might want to do, and you can just think about this and figure it out, you'd come to this answer yourself, I'm pretty sure, is you'd want to just take a big plot of land and then break it up into a bunch of different plots that are 100 square meters. And then what you'd want to do is randomly say, so what do I have here? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So I have 30 plots of land. I might take half of them and apply fertilizer to them and leave the other half without fertilizer. Now what I don't want to do is say apply fertilizer just to the 15, 1, 2, 3, 4, 5, 6, 12. Maybe I just take these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So maybe I just would do it on that outer horseshoe. Well, maybe there's something special about the land on the perimeter for some reason. Maybe land next to it has some special characteristic that makes things grow faster. In that case, I'm not going to be picking up the effect of the fertilizer. I'm going to be picking up the effect of that other factor that we're not measuring. For some reason, maybe this gets more care. People who are going around pulling weeds out, maybe want to keep this weed free. The people pulling weeds out do a better job on the perimeter because they're not having to step and be careful where they're walking and things like that. We don't know. And so what you don't want to do is have any systematic bias in where you apply your treatments. So you'd want to just randomly treat these things. Take some random number generator and let it tell you which 15 that you ought to choose. 7, 8, 9, 10, 11, 12, 13, 14, 15. Let me just pretend like it came out over here somewhere. 15. So now we've got some plots on the border that are treated, some that are untreated. We've got some in the interior. We've got a little place here that doesn't look too random, but that's just because I was doing this out of my head, a real random number generator. And if you had a lot more plots, a lot bigger plot, so I have 1,000 of these with 500 of each type, we're very unlikely then to get systematic biases. And so that's what we mean by a randomized ideal experiment. This is a randomized controlled experiment. And then you want to be sure as much as you can that each plot of land is treated exactly the same. It gets exactly the same amount of sunlight, exactly the same amount of weeding, exactly the same amount of water, and things like that. So that the only difference across these plots that's systematic is whether or not they've been treated with the fertilizer or not. Then, of course, what you would do, you would then look at the yields, the average yields on the treated plots, look at the average yields on the untreated plots, and then your hypothesis is that one's bigger than the other. You could then test statistically whether there was any significant difference between those that are treated and those that aren't. And that's what you would want to do. And you could do that all through a regression model, as we'll see later on. So you have a randomized control experiment. There's a treatment group. Those are the ones that get the fertilizer. There's a control group. You always need a control group. You can't really estimate a causal effect unless you have somebody who was untreated. So you need a control effect. You might be able to treat everyone and give different amounts of fertilizer to each plot. So you could randomly assign, so many here, so much here, so much here, so much here, and see if when you get more fertilizer, do you get more yield, and what's that relationship? So that'd be another way you could do this experiment. But again, for the most part, the way you do this is you need a treatment group and a control group, and the treatment needs to be assigned randomly. Often in economics, one of the problems we have is that the treatment is not assigned randomly. And that's going to create problems for us because we're going to have to worry about controlling for other things. If all of them were assigned on the perimeter, like I was first doing, all 15 X's are on the perimeter, and these somehow get more weeding, if we had a variable that could control for that, we could add it to the model, and then we'd have a multiple regression rather than a bivariate regression, a two-variable regression, because we'd have not just, here's yield on one side, we want to know how does yield depend upon fertilizer. We could also say how does it depend upon weeding. If they got differences in water, how does it depend upon water? So as long as, if it's not random, then we're going to have to try to control for all these other things that we couldn't control for in our experiment. So in economics, we just have to take the data that's given to us from the world. It's historical data, and it may not have been randomized. And when it's not, we're going to have to learn how to handle that situation. But ideally, this is the kind of thing that you would want to do. So a causal effect, what's the definition of a causal effect? The book defines it as follows. So a causal effect defined as the effect of a treatment. I think you probably have this in your head already. Effect of a treatment on an outcome of an ideal randomized controlled experiment. Controlled just means all else equal. So as I said, it's easy to imagine an ideal experiment for class sizes and other sorts of things, but we're not going to have those ideal experiments in economics. When we do the class size thing, we'll see that we don't necessarily just randomly assign different class sizes across different schools and different grades and that sort of thing, and then look at the outcomes. And so what do we do if the data are not random in that way? Suppose that the schools in wealthy districts tend to have lower class sizes than schools in less wealthy differences. And the kids in the wealthy districts have advantages. They can take classes outside of school. They have other parents could hire extra teachers and tutors and things. Maybe they do fundraising for the school that gives that school more money that the poorer schools can't do. Then we're going to have to figure out a way to control for all of those differences. It's not just class size that varies across schools. It's also going to be wealth levels and demographics and things like that. One of the variables that will be important in here is it will be socioeconomic variables. Suppose we have a lot of immigrants, for instance, who don't speak English in one district. These are districts in California. And in another district, there's hardly anyone who doesn't speak English. They're all native speakers. Well, then there's a difference between those two schools. And there may also be class size differences on average. If we don't control for the percent of immigration, we're going to get the wrong answer about the effect of class size. And so ideally, we want these randomized, controlled, all else is equal. They all have the same amount of immigrants. They all have the same amount of wealth levels. All else is equal. But in the real world, all else isn't equal. But multiple regression will allow us to control for these other things, and it's as though they're held equal. And so we'll see how that all works. Okay, so that's about the first three questions, which were about causal effects. What about the fourth question, which is about forecasting? There, the things work a little bit different. So let's talk about forecasting and causality. In particular, whether you need causality to do forecasting. Is it important that one variable causes another if you want to do forecasting? Does there have to be causality? And the answer is you don't need a causal relationship between two variables to make a good forecast. And I'm just going to steal the book's example here because it's simple and pretty straightforward about how this works. So in the previous questions, if there's a causal effect, that's a question about causality. There needs to be causality, or we're going to get the answer that there isn't. That makes sense? I hope so. But here you don't need causality. So suppose we want to know if it's hot outside, or what the temperature is. Is it hot out? I can look at the number of people wearing shorts out my window, and if there's a whole bunch of people wearing shorts, it's probably hot. If there's a whole bunch of people wearing coats, it's probably cold. But whether you wear shorts or whether you wear a coat, wearing a coat doesn't make it cold. It's not causal. In fact, the causality runs the other way. It's that being hot causes you to wear a coat. But I can nevertheless use the coats to forecast whether it's hot or not. I could use a number of shorts to forecast whether it's hot as well. And so even though the causality runs from the temperature to what you're wearing, you can look at what you're wearing, which has no causal effect at all on the temperature. Wearing shorts doesn't make it hot, but nevertheless, shorts are a good variable to use to forecast whether it's hot or not. And so, is it hot? I look at the temperature gauge. Oh yeah, it's hot. I'm using that to forecast, but that gauge didn't cause it to be hot. The heat caused the gauge. There's usually a correlation between the two variables. There is. That's why you can use them, but it doesn't have to be a causal relationship to do forecasting. Okay, now let's next talk about different types of data. So data, and we're going to talk about sources of data and types of data. So the sources part, I'm just going to make clear what I've been talking about between experimental and observational data. And here we'll talk about the different types of data you can use in econometrics. So the first type of data, so these are the sources of data. So there's two sources of data in the world. That says two sources. It's not written very well. That's not a very good W. But anyway, it says two sources. The first is experimental data. And that's the gold standard. That's what we want if we can get it. Often we look in economics for natural experiments where for some reason we get randomized treatments even though it wasn't necessarily intended. Sometimes they'll do a lottery on who gets into certain schools or something like that. And so we can use that lottery, which is a random assignment mechanism, as a way of performing a natural experiment, even though they were just trying to be fair by randomizing who gets to go to what school. You can use that randomization as a way to perform a natural experiment. But so obviously that comes from experience. Obviously, these come from experiments that are hopefully well designed, control for the right things, so on and so on. But these are difficult and costly in econ. I mean, we can do some of this. You can take students to a lab and give them different amounts of money and let them do this and that on the computer or something like that. But the notion that I could take the Great Recession and run it again and again and again, and each time give it a different treatment. So I want to know, does government spending matter? Great big controversy during the financial crisis and that recession that followed. So I say, okay, this time I run the experiment, we're going to have this big recession, and I'm going to do this amount of government spending. This time I'm not going to do any. This time I'll do this amount. This time I'll do this amount. And we can use those repeated experiments to then figure out whether government spending matters or not. But what we actually have is just one experiment. We have one time that we ran the data through. We can't run a Great Recession over and over and over. It's just not practical. There's no way to do it. And I have one treatment. They did a stimulus package. How can I use that non-random data then? The question is in economics then, we don't, because experiments are difficult and costly, we're not going to have these experimental data for the most part. As I said a minute ago, sometimes you can find natural experiments, and that's great. That's very useful, but for the most part, what we have is observational. Non-experimental data. I'll often use the term historical data. So it's just from surveys, historical records, it's actual real world data. It's just what we get. Here's what GDP is, here's what consumption is, here's what taxes are, and we just have that one set of data, and we just have to do the best we can with them. And those pose a major challenge when we're trying to estimate causal effects, because we don't have this ideal relationship. And then we're going to have to worry about how we can put in things to control for all these things we would have controlled for in a natural experiment that weren't necessarily controlled for in the real world. So how do we get those controls in it? So a lot of economics and econometrics is devoted to figuring out how to handle this case. If you can do experiments in the lab, I just want to know, if I change the temperature, what happens to the combination of these two chemicals? Does it get bigger or lower? As I raise the temperature by 10 degrees, does this chemical reaction happen faster or slower? I can do that thousands and thousands of times in the lab. I can systematically change the relationship. I can make sure that air pressure and all sorts of other things besides heat are exactly controlled for. So the only two things varying are the chemicals combining and the amount of heat, and everything else has been controlled for and is equal in a well-designed experiment. Then it's fairly simple to do the statistics. You don't have a lot of issues. If I just take those, if I just go out in the real world where also, the temperature's different, and there's wind, and there's all sorts of other things going on, and I take those kinds of data and try to do the same kind of analysis, it's going to be a whole lot harder. And it's that second world that economists live in. Okay, both experimental and observational data come in three types. So there's three main data types in the world, no matter how you get your data. And the first is called cross-sectional. And this is data on a collection of objects, of people, firms, etc., at a point in time. So the date might be January 2014. And I'm looking at consumption across a bunch of different individuals. So individual A has some, this is a number, B, C, D, E, they all have numbers. So this is a cross-section, a whole bunch of individuals, their level of consumption. I might also have their income. At every point in time. And I probably want x and y the other way around. Oh well. So it's at a point in time, and it's a whole cross-section of individuals, or it might be sales across firms. You might take all the 7-Elevens in Oregon. What were their sales on this day or within this week or some time period? And so it's a specific time period and a whole cross-section of individuals. Time series data is the next type. And it's just the opposite. I'm mostly a macroeconomist and a macroeconometrician. These are the kinds of data I encounter most frequently. This is data on a single series over time. So how did I say it here? Yeah, data for a single entity. Over time. So I might take some individual, look at 1, 2010, 2, these are months, 2010, 3, 2010, all up to maybe 1, 2014. So I have, this is for an individual, and maybe I'm looking at that individual's consumption over time. So C, C1, C2, C3, or C whatever, CN. Actually, in time series, we use T's, CT. So there's maybe T's 100 or T's 50 or something like that. So GDP, first quarter it was this, second quarter it was this, third. GDP is a time series. Consumption for the aggregate economy is a time series, if I just follow it. If I look at investment over time, that's a time series. And so one is at a point in time, it's a whole bunch of people, a whole bunch of entities, their consumption and income at a point in time. This is consumption and income over time. So you might have Y1, Y2, Y3, YT. So this is consumption and income in January 2010. Consumption and income February, March, all the way up to January 2014. Something like that. Okay. So that would be a time series of data. Then there's something called panel data. And it's a combination of both. This is when you track a cross-section over time. So the date, 1, 2010, 2, 2010, 3, 2010, up to, say, I don't know, I'm using 1, 2014. There's no real reason to stop there. And then I have person A, B, C, D, and I'm looking at consumption. So I look at this person's consumption at every point in time, this person's consumption at every point in time, and so on. E, and so on. There might be a bunch of people. So this is the cross-section. At 1, 2010, there's a cross-section. We have 5, I didn't write E here, but we have 5 time series in this direction, and together that's called a panel. So a panel is a cross-section of individuals tracked over time. I didn't say this earlier, but for cross-section, the number of observations is usually given as an N. For time series, it's usually T. So for a panel, what is it? Well, I've got T, this would be XT, this would be X1, and so on. I've got T time series observation, and in this direction, it would go to N. I have N in the N observations in the cross section, T here. So the number of observations here is equal to N T. Okay. We will mostly work with time series and cross sections. Panels bring up their own special issues that are probably best left to 421 and even beyond. There's some very complicated things associated with panel data that you don't have in the other two types. And so I will let whoever teaches you 421 do their job and teach you about panels. I'm going to mostly talk about cross sections and time series, where the simple regression techniques tend to work. Well, that's the end of the introductory material, and thank you.